Right, so Bismillahirrahmanirrahim. Welcome to the fifth lecture on Z-Transform, right? We have had quite a journey with Z-Transform. कहाँ से start किया था हमने?
सर सॉरी वो जो लेक्चर हमारा मिस हुआ है सर ट्यूसडे वाला
हाँ उसका कर लेते हैं ना प्लान. अच्छा. Z-Transform. What have we done so far? क्या क्या आपको याद आता है? Quick recap. Especially what was the last lecture about? तो लास्ट वन पे क्या किया हमने पिछले लेक्चर में? यूट्यूब लिंक खोलना पड़ेगा. कुछ किया था ना, एक ही टॉपिक था. नहीं, उससे पीछे inverse Z transform. Yes, so we did the mostly the inverse Z transform. Properties part we just revised a bit, but the practice we did before that. Right, the last lecture was mostly on the inverse Z transform, and of course every lecture includes some revision of previous ones, so we might have discussed that. So before I close Z transform today is the last lecture on Z transform. We've had the background, we have the definition, we have had some practice problems in finding Z and inverse Z transform, right? Today I will wrap up Z transform, connecting it to something that you have already seen in some places, and let's say another interpretation or way of looking at transforms. Okay, that way is how mathematicians and physicists usually use the transform. So we will come to that today and close this. But before that, I would really like to get a feel for what do you think you know about Z transform by now. Before, when you joined after the mid, right? You didn't know anything about Z transform, right? It was first thing for you. Now you've had 4 lectures on that. Today is the 5th one. So by now, क्या वो हम के ठहरे अजनबी इतनी मुलाकातों के बाद, right? So are you still strangers or you know something about the Z transform? क्या जानते हैं आप अब? Anything?
Convolution to easy कहते थे.
Converts convolution into product, makes it simpler. Good. Or time to it converts from one way of looking at data to another one, which we often call the transform or the frequency domain. Good. What else? You now know the definition of the Z transform, and you know what is Z by now. What is Z?
Any complex number.
Any complex number, right? And for a particular sequence or signal, Z may be restricted to some range. What's that range called? Region of convergence. That region makes sure that the Z transform definition is a convergent series, right? Okay, that's good. So you know lots of things by now, right? And you've seen pairs of Z transforms. You have seen some properties of Z transforms, right? So can you mention one pair Z transform from time to Z? Any? So
Delta N.
yes. You know the notation by now. In general, if time is xn, discrete time, then Z transform is capital X Z. Right, so you say delta n, yes, that is a very useful one. What it becomes? 1. Yes?
U of n.
Which one?
U n.
U of n, yes. What was that?
Z by z minus 1.
Z by
Z minus 1.
Z minus 1, right? And then you've also seen some properties, right? Like convolution becomes product. Delay, what happened to delay? So if I had u n minus m, what happened? You were able to
Z power
multiply the whole thing, whatever un, whatever was the Z transform of un, the Z transform of un minus n is that same thing, ये डिब्बा box है ना, this box times a multiplier. What's that multiplier? Z minus m. Where is this minus m coming from? Here. Yeah. So those were properties. With the help of properties and pairs and definitions, we were able to practice doing some Z transforms, right? How many methods did I mention? Usually we use three. What are they?
Partial fractions.
Yes. Partial fraction for inverse Z transform, right? For Z transform, computation meaning MATLAB, other languages. Then there is by definition. Third one by form pairs and properties, right? Third one is by far the most common. You have tables of common properties and common pairs. Then you use them to solve for more complicated combinations of those, right? Okay. For the inverse, as you said, again using computers, MATLAB, or partial fraction expansion, or there is long division also. I left long division as an example or as a reading exercise for you. For partial fraction expansion, what were the steps? If we can just do a very quick revision of that. So you have to find, you are given x, z, right? And you have to find x, n. This is inverse Z transform. Now the definition, if you remember, involves a contour integral, right? Which is usually hard to implement, or if you try to implement numerically, then you're going back to MATLAB, right? So here in partial fraction expansion, how did we do the inverse Z transform? So there were three steps, right? First one was apply the partial fraction expansion to not xz but xz by z. Okay, if you do it on xz, you're still okay mathematically, no big deal, but the outcome comes more elegant usually if you divide it by here, and then what do you do? So yes, once you have done the partial fraction expansion, that means on the left side you have just one term, numerator denominator. On the right you have multiple terms, each with one root, right? That's what partial fraction expansion does. Then you multiply out by z. What does this step do? Removes the effect of the artificial change you made. Mathematics does not allow you to change things, right? Equation यही होती है ना, बैलेंस है, एक तरफ पे 2 ऐड किया है आपने, तो वो साइड बाहरी हो गई, ऐसे. So you have to then do something to the right, otherwise you have to say this is not an equation now. Yeah. So you cannot do things artificially. You have to take away that effect eventually or justify it. Then third one, use tables to get the inverse Z transform, and the most common one that you end up using was Z over Z minus gamma, right? That is gamma n u n kind of thing, if I remember correctly. That is what you had, yes? But there could be other forms also sometimes. Usually it's that. And I gave a solid example of that for which case of roots?
Real and distinct.
Distinct real roots, right? And then I said you should also know a bit about repeated real roots. These are the only two cases you need to know for this course. This is just to give you an idea. We're not repeating the whole thing, so you don't need to do like complex conjugate roots and more complicated cases. So what was this? We had xz was 8z minus 19, z minus 3 times z minus 2. This is your Z transform process in the transform domain, you want to find it in the time domain. What's the first step? Apply partial fraction expansion to xz over z. So the first thing we did was introduce another root here. Yeah? Now you see, okay, this is a case of distinct real roots. How many roots? 3. So you write it out so that each function gets, each term gets one root, right? Plus c z minus 3. Right? And this thing, this whole thing, we named it fz for our convenience. Then what was the value of a? You can just test in many ways. You will find this result holds. What was it? To find a, multiply fz with the denominator of z. Whatever is left, you solve it at the root of this one. Yeah, that's the crux. So to get b, what would you need to do? Multiply fz by z minus 2 and put, after multiplying, put z equal to 2. Okay, so that way you can find a, b, c. So in our exercise last time, I'll just skip the steps. We found a to be minus 19 by 6, b was 3 by 2, and c was, do we have c? Yes, 5 by 3. So then you can claim, okay, now I have this, let's replace a, b, c here. Yes, so a is minus 19 by 6, b is 3 by 2, c is 5 by 3. Yeah, what's next? Second step is just, so far you've done the first step, right? Apply partial fraction expansion to xz over z. That's what you've done, found the coefficients. That's first step. Now you do the second step. What was that? Multiply out by z to take away the effect of what you introduced. So if you multiply out by z here and here, you're back to xz, and then this thing becomes what? It's minus 19 over 6 plus z times, so 3 by 2 times z over z minus 2 plus 5 by 3 times z upon z minus 3. Now you are back to xz, but in a much nicer notation compared to the original. Yeah, इधर से समझ नहीं आती इसका inverse z क्या होगा, but from here now it's manageable. You already know this is, there is a unit
Delta n.
yes, so it's delta n and the multiplier remains where it is, so it is delta n plus 3 by 2 is just a multiplier, constant value stays there, but this has a particular form. What was that?
Unit step.
Yes, will multiply with gamma. We had that formula, right? So I will write it out again for you. Remember, this is the result we mostly use. Gamma n times un equals, corresponds to, just keep this one in mind, yeah? Corresponds to z over z minus gamma. So by that standard, what is this? Gamma square, right? Sorry, 2n. Gamma is 2. 2n, and then what? Un, yeah? Plus 5 by 3, 3n un. This, now you have found your process in the time domain, because notice no more z here. Yeah, all of it is now x n. You give me one value of n, I can give you value of this process. Let's say you want to find the process at x equals 0, right? At x equals to 0, this is 1, so you have minus 19 by 6 plus 3 by 2, 2 raised to 0 is 1, u0 is also 1, plus 5 by 3, so basically x0 is minus 19 by 6 plus 3 by 2 plus 5 by 3. So any n you put here, you can get the time domain values of your process, right? So this was a very quick revision of the inverse Z transform, right? Now we go to the last topic of Z transform that we will do in this course before we move on to other topics. Remember when we went to the LTI thing, we started with a question. What was the question?
What happens to an arbitrary input when it goes through a system?
Yes. So another way of saying it is how to tell the output of a system to an arbitrary input, which is what you're saying also. What happens to an arbitrary input as it goes to an arbitrary system, right? So there is another question that people have been asking related to that, and actually that question forms the, in a way, foundation of a lot of modern machine learning, data analytics, data science. A lot of that is based on this question. Okay, so I've mentioned this before. You should see this course as your first introduction to actually data analytics, machine learning, and everybody is going to use those now. Just like you use MATLAB, everyone will soon be using more advanced techniques coming out from machine learning, AI, data analytics, right? So everybody should be familiar with those. In fact, this week's lab will be on practical machine learning, signal feature extraction. You will see it's very simple, nothing complicated. We don't want to scare you away, just give you a taste of what's going on. But for now, the question I want to answer, a lot of great discoveries start with a great question, right? So this is an important question. How to model, I'll write it and then I'll discuss it with you. A system from history of inputs and outputs. So you have a system, could be mechanical, it could be electrical, it could be human, like people responding to things, it could be financial, like stock market, right? And you want to see, okay, if you could model it using basic physics and everything good, but usually that becomes pretty hard. So what you can do is probe the system, send it input, see its output, then send it another input, see its output, then send it another input and output. Now the question is, sorry?
Serial and serial out.
Right. So you have to send different kinds of inputs, right? What you want to do is say, now I want to model this system based on history of its inputs and outputs. Why that? Because often it is easier to get these. You send an input to the system, you know what input you send, and you measure the output at some point, right? That's it. The system itself is a black box for you. Now if you could do that, imagine how powerful that would be, right? Because all you need is a history of inputs and a history of outputs. So let's see. I'm going to make 3 claims here, and then I'll justify the claims one by one. Claim 1, output of LTI systems. You don't need to write the whole thing, but I'm just writing it out here just to emphasize. Right? I could just speak it out also, but it's good that you remember this, how we got to where we are going now. Output OP of LTI systems can be modeled as linear combo. Combo reminds me of Tekken. कौन खेलता है अब? अभी तक खेलते हैं? कौन सा वर्जन चल रहा है? When I bought PlayStation, we had Tekken 2 coming out, and I played till Tekken, I don't know, 4. Then I just grew too old for that. It got too flashy ज़्यादा हो गई. शुरू वाली थोड़ी सुकून वाली थी, and that's what older people always say. Everything seems too flashy when you are older. Okay, can be modeled as a combo of inputs and outputs. That's a very big claim, right? But that's also a beauty of LTI systems. They can be modeled in most cases as linear combination of their inputs and outputs. Okay, so this takes away this concern that is it even possible. So yes, for LTI it is possible. That's the first thing. Second claim, the above approach leads to difference equations. You know what's a difference equation? No? You know what's a differential equation?
Yes.
So then what's a difference equation? Differential equation, difference equation is the discrete time counterpart of differential equation. Differential equations occur in continuous time. Their counterpart in discrete time is difference equations, and you have already seen some difference equations. For example, if I write that the output बड़ी entry आपने गिरते पड़ते entry सब busy yn, if you have this, that yn is axn plus bxn minus 1, for instance, this kind of equations which are in discrete time, and then there are delays of time or advances of time, are called difference equations. And in fact, when you discretize continuous equations or differential equations, they become difference equations. Okay, so you know them, you've seen them in this course also, but now you have a name for them also. Difference, then it becomes differential, and it's continuous. Yeah. Okay, so claim 2 is that if you take this approach, what is this approach? Modeling LTI system as a linear combination of its inputs and outputs. Yeah, then you have, if you do that, you will end up with difference equations. Okay, third claim, claim 3, Ztransform helps represent and solve difference equations in an elegant way. Okay. if you have, for example, if you have y equals, let's say, 2x plus 3c or something, yeah, that would be called a simple algebraic equation. So we will come to that. But the third claim is Ztransform helps represent and solve difference equations in an elegant way. How it does that, we will see that today. It converts a difference equation into a simple algebraic equation. Okay, it's going to convert a difference equation into a simple algebraic equation, and you have learned to solve simple algebraic equations, so it will become much easier. So let's see what's going on. I'll have to raise this, but I think you will remember. Firstly, the question we're trying to answer: how to model the system from history of inputs and outputs. We say that for LTI system it is possible, and it will actually be a linear combination of inputs and outputs. That's one. Secondly, we say if we do that, we end up with difference equations. Third, we are saying to solve these difference equations, Ztransform is going to help us. So now let us take a look at the whole thing. Let's say you have a system that you want to model. You know it's LTI somehow, or you'll have to prove that it's LTI. But then, let's say you have collected the inputs and outputs. So let's see. You say I gave it input xn, and it gave me output yn. Okay, and you say I gave it before that an input xn minus 1, and it had given me an output yn minus n. What's going on? This is a history of how you interfered with the system and how the system responded. Right? Humans में भी होता है ना, ये बात कही तो उसको गुस्सा आ गया, तो फिर आपको पता चल गया आप कैसे गुस्सा दिलाना इस बंदे को. Right? So, but human systems are highly non-linear, non-ergodic and everything, so this won't hold for very long. They are smart, they will adapt, और उनको गुस्सा आना कम हो जाएगा, फिर आपको छोड़ ढूंढना पड़ेगा. Right? But what you do is like this, yeah. So let's say you have collected. Now this is a debatable thing, or it actually depends on the system, how long a history you need to record. Okay, but in machine learning, in AI, they call this training data. Right? So how much training data you have for the system. Here we have, let's say, up to n. The sum n, we don't know how many. It will actually depend on the system. It's a question for another course. We won't go into that too much. Let's say n is sufficiently large. What is the meaning of that? Maybe we'll see it sometime in another course. So now, why is the history of inputs and outputs important? So let's see. I think we cannot have it in the camera, but I'll show you here. Let's say this is a system. Yeah. What is this system? It's some mass placed on a table, right? So let's say its positions are the outputs. I'm able to measure its position where it is. Yeah. And the input is how much I push it. Yeah. So I say, okay, if I pushed it this much, it went here. If I pushed it this much, it got here. I record my inputs and the system's outputs. So that's the history of inputs and outputs. Now, why does the history of input history make some sense, and why does the history of output also matters? See, the output can show some internal dynamics of the system. If I give it the same 3 pushes, but this was pinned here, okay, would it do a translational motion or a rotational motion? If I give it the same 3 amounts of pushes, see, it's doing now rotational. before it did translation. So the systems, the way the system state is evolving, its position is evolving, also depends on its internal dynamics. Yes, so the output also has quite a lot of information about the dynamics of the system. If it starts rotating, this is just one example. Yeah. Um, Similarly, there could be more advanced dynamics that are hidden in here. Okay, so it makes sense to go for both the history of input and output. And now, as we said, that the LTI system can be modeled as a linear combination. अभी तक आपको linear combination तो पता चल गया होगा. So what is the position of the system at time n? If before this I have given it 5 pushes and I got it at 5 different positions which I know, then at the 6th input, where is it? What's the output? That actually I can model as a linear combination. जो input अभी दिया है, the last input I gave plus some weighting with my previous input, okay, plus linear up to, as I said, we will go up to say sum x n minus n. Okay, again keep this in mind. I'm asking you, when I say yn, let's say this is y3, what I'm saying is where is the pen if y is the position. Okay, where is the pen after 3 pushes? Yes, so you need to know the history. Only knowing the third push is not enough, because you need to know how much it has traveled from the start. Then you will be able to say where will it be after the third push, right? Then, as I said, history of inputs is not enough. You need history of outputs. Why was that? Remember, same pen getting same pushes can go straight here, or it could be rotating. Then your output here of the position has to be different from this one. So we bring in the history of outputs as a linear combination. Traditionally we write that with a minus. It's just convention. You will see why that is. Actually we would want to take this to the left, that's why. Otherwise you could make it a plus and absorb the minus. Here it's not rocket science, okay? It's just based on experience, makes it more elegant, that's all. A n y n minus n. So what happened now? I collected a history of inputs and a history of outputs, right? And then I wrote the current output as a linear combination of the past inputs and the past outputs. And I already said or claimed that you can do this for LTI systems. For others, we have to argue what you need to do, but at least for LTI, it is possible. What was the second claim? This approach would lead to difference equations. Is this a difference equation? Yeah. It is, right? And difference equations can be a pain to solve. I will show you today. You only can solve them iteratively. It's not very easy to solve these. You have to iterate because there is time delay going on. Yeah. So what was the third claim? The Z-transform can convert difference equations into simple algebraic equations. Let's see that now. And there is a property of the Z-transform that helps us with this. Can somebody tell me if xn has a Z-transform xz? Yes. What is the Z transform of xn minus 1? Z power minus 1. This was the shifting property, yeah? Whatever you had originally, that will be here, and multiplied by the factor and this minus 1 is coming from here. Now this has an indication for us. Notice we could get rid of all of these in the Z transform domain. Let's take a Z transform of this. Yeah. So if we do that, what is YZ then? V naught x Z, right? Z transform is linear, so you can apply it to each term separately, no issues. Plus, can anybody tell me what this is?
B1 Z minus 1.
Yes, B1 Z minus 1 x Z. Notice no more shift. This is not difference equation anymore, right? Just algebraic. So plus B2 Z minus 2 x Z plus so on Bn Z minus n x Z. What happens to the this side? This part? A1
Z minus 1 YZ.
exactly, Z minus 1 YZ plus A2, sorry, here the minus here, minus Z minus 2 XZ and so on till habit of writing plus, okay, AN Z minus N Y Z, right? Now firstly, this is no longer a difference equation, there is no delay or anything. First, second, you can actually make it more compact now, right? If you take all these minus terms of YZ to the left, yes, what do you get on the left? You have YZ times what? A polynomial, yes? So let's see, yes. You have YZ times 1 because of this, and this term comes here. You have A1 Z inverse YZ. Now you see why we had a minus. Now it becomes plus. That's it. It's not a big deal. So plus A1 Z inverse, right? Plus A2 Z minus 2 plus AN Z minus N. That's what happened to the left hand side, this YZ side. What about this part? What does this become? XZ times B0 plus B1 Z minus 1, so on until Bn Z minus N. Right? Now this is in a way looks like the Z transform of the sequence A1, A1, A2, AN, right? And this looks like the Z transform of the coefficients B0, B1 of that sequence, right? Let's give these a name. This whole polynomial in Z, let's call it as in literature QZ. Okay, and this one we call it PZ. We will know now why one is P and why the other is Q. Then can we write a compact notation connecting the input to the output? Can we do that? So we want to write YZ equals something with XZ. What is that something? Can anybody? Nazar? I've already given these names, right? So use those instead of the whole thing.
Like QZ.
Yes. PZ over QZ, right? That's a rational function. P over Q होता है इसलिए ये PQ नाम है. Yeah. So what happened just now? You have written the output, right, as a simple product of the input with some rational functions, which is actually just simply based on the Z transform of the coefficient polynomial, right? That's it. Now we will see an example of how to solve these things, but notice that by the way, we can now, what we can do to solve this, to, for example, if you wanted to find something for a given xz, or you wanted to find this thing, how does it look? You can take the inverse Z transform using partial fraction expansion. So all three claims are here. We were able to, or we wrote the output as a linear combination of inputs and outputs. That became a difference equation. Using Z transform, we converted the difference equation into an algebraic equation, right? And then we can use or solve the algebraic equation to get whatever parts we need here. Okay, but let's see. Let me bring home this point with the help of an example. I'll let you solve this very quickly, so you can give it a shot. यहाँ तक कोई question है अभी? There's a lot to digest, right? I've tried to break it down in a way that when you go through it again, you should start seeing more clearly, yeah? But for now, let's see, with the help of an example, and we'll end today's lecture after that example. What we did just now is also very critical. It's one of the most critical questions of this course. The first one was how to give the output of an arbitrary system to an arbitrary input. The second one was how to efficiently write process, right, in the eigenfunction domain, which led to Z transform. This is the third one. So if you understand these three, I think you have learned a lot in this course. The rest is more just practice. Right, so let's take an example. You have a discrete time system described like this, and I'm just going to tell you without having to ask you if it is LTI or not. I'm just going to tell you it is LTI. Okay, let's accept that. Now I want you to solve this system for xn equals delta n. What just happened? I gave this system an input. What's the input? Impulse, yeah, plus delta n, and I want you to find the output. On your way, you will need something called, what is this? Anybody remember? Initial condition, right? And solve for xn equals delta n. When we say solve, I mean find yn for n greater or equal to 0. So I want you to find y0, y1, y2, and hopefully a general expression for this. कर सकते हैं क्या आएगा? फिर try करें. कैसे करेंगे? Firstly, anybody can notice that this will be solved iteratively. Right? That's the problem with difference equations. Even an equation so simple as this one has to be solved iteratively. It becomes a headache. Imagine if there were 20 terms of x, xn minus 1, xn minus 10, and 20 terms of y. This would become really crazy. That's where Z transform will come to the rescue. We will see. But for now, just to help you see the pain in solving it iteratively, just try a little bit. What do you get? Y0. What's y0? y0 is कोई नंबर है ना, क्या है इसलिए निकला? Do you know how to get started for y0? y0 is 3 delta 0 because xn is delta n, so y0 is 3 delta 0 plus 0.8 y minus 1, because if you put n0 then it's 1. Do you have y minus 1?
Yeah.
Let's put that here. Do you have delta 0?
So 0 हो जाएगा.
Delta 0
One.
एक ही जगह तो 1 होता है. जब उसका आर्ग्यूमेंट पूरा का पूरा 0 हो जाए तो डेल्टा 0 1 हो जाता है. 3, yes, so y0 is 3 plus 3 plus 8, yes, 0.8 times 10. 10 कहाँ से आया? Initial condition से. So this became 11. Now what's y1? Back to this thing. So कोई हल ही नहीं है, right? Every time I have to go back to this to do it iteratively. So what's y1 now? y1 is 3 delta 1 plus 0.8 y0. Right? What is that? Delta 1 is 0. 0.8 times y0. What's y0? Now you have it. Right? इसीलिए iterative solution है. Next step is using the previous result. Yeah. So 0.8 times 11, whatever that comes out to be. So if you keep doing that, what do you get in y2? Any guesses? I will cut to the solution. You will find that it's 0.8 square 11. You can now try to guess what is yn. What is it? 0.8 raised to n times 11, right? And since all of this holds for this, we can make our life easier. Instead of writing this every time, we can write multiply with un, right? That's a shortcut. Okay, so this is your solution. Now let's see if we didn't want to go this way and wanted to do it with Ztransform. Okay, so how do we do it with Ztransform? Okay, take the Ztransform of both sides, right? What's the Ztransform here? Y z, yes, equals 3x z plus 0.8 what?
Z minus 1 yz.
Z minus 1 y z. I can take the yz thing to the left, right? What could that lead to? Yz times what?
1 plus 1 minus 0.8. Z minus 1.
Equals 3xz, right? 3xz. But I want yz here alone. Yeah? So I can send this over there. So if I do that, I have yz equals 3 over 1 minus 0.8 z inverse xz. Right? Now I have y now, but it's not in the right domain. It's in frequency. I want it in time. What do? Inverse Ztransform. Inverse Ztransform, because this is only single root, you don't need to do partial fraction expansion. You can just simply take what, if you multiply and divide by z, what happens? Just to make things easier, it's 3z over z minus 0.8, isn't it? Yeah? So you can do that. याद है हमने लास्ट टाइम ये एक ट्रिक किया था कि 5n plus 1 un, we made it 5n times 5, right? So you can play a bit of tricks here. So you get 3z, z and 0.8. Now just by looking at it, you can tell me the inverse Ztransform of this bit, right? I forgot one thing, sorry. xz. What's the input?
Delta n.
So what should this be?
Nothing.
1.
Yeah,
Not nothing.
Yeah,
Nothing is different from
yeah, same.
1. Yeah. So actually your output is this. All you need to do is get the inverse Z transform of this part. What's the inverse Z transform?
2 to the power of 0.8.
3 is a multiplier, right?
Multiplier.
Then you have Z over Z minus 0.8. So 0.8 power n un. Isn't it? You have, I'm out of space here, but isn't it like Z over Z minus gamma has Z transform? Gamma n un, right? So this is the form you have, Z over Z minus 0.8. Gamma is 0.8. So 3 remains point, but where are we? 0.8 and did we miss the initial condition somehow?
What would be?
Yeah.
Yeah.
3Z over Z minus 0.8. Let's see if we miss the initial condition. Yeah. 0.8 Z inverse YZ. Where is that? Yeah. So, I think I forgot to mention the initial condition. You can see in the table of Z transforms, if the initial condition is not 0, okay, then it has to show up here. we skipped that briefly to make things simpler, but you will see that in the table. So actually we do have, what is the initial condition? 10 here, yes. So then we will have 3 plus 8 there, yz will be 3 plus 8. Yeah, so this will add another term that we skipped, okay. Just redo it with this term added, and you will reach the exact same solution, which is going to be this thing, 0.8 n 11 times un. This 3 will add to the 8 to become 11, okay. So we had a 3 here, but this additional term 8 plus 3, correct, z is 1. So you will end up with the same solution. Now what does that tell us? With the help of Z transform, what did we do? We converted this difference equation into a simple algebraic equation, right? And instead of having to do this whole thing iteratively, we simply solved it directly with the inverse Z transform, right? Now if here the gain isn't very big, you could just see the pattern, but if there were like, and in reality there can be like 20-30 terms of these, then things become really crazy in the difference equation, okay. Then converting it to algebraic equation helps a lot. So this is in fact another interpretation or way of looking at the Z transform, and this is the result that they often use in mathematics. In differential equations, the same thing is done by Laplace transform, okay. So we will discuss that next time, okay. Right, let's see. Okay, any questions? There should be some. No?
Sir, वो
मैं recording बंद कर